happening. I don't know what it is. That's it. Okay, perfect. So let me introduce now the second or last speaker of this morning session, which is the talk by Daya from Delhi, my friend for many, many years. And he will be speaking today on the Wess-Zumino model in the context of supersymmetric field theory. So Daya, please, the time is yours. With additional minutes you took from
Thank you so much. Yes, great. So, I'm very happy to see you there on the chair, and I special thanks for donating me some more minutes, because I always have too much to speak. So anyway, I extend my heartfelt thanks to Milo, to Vladimir. All of them are so cooperative and so helpful to me. Actually, they even in the last 2 days, Vladimir and Vit were very kind to me to educate me on how to make proper use of this Zoom platform. I wasn't probably able to do it, so now I'm very happy that I should be able to do it more properly. That's very good, great. So are my slides visible?
Yes, it's okay. You may continue.
And there is some additional problem. When I put my slides on, then my camera automatically becomes muted. I want to keep it unmuted.
You are unmuted. You may speak. Yes, you are accessible to the auditorium. Yes. Now I see your picture also. So you now it is presentation, full-fledged presentation now. Yes.
Yes. And is it possible to put this? Okay, is it possible to put the view in the side by side? Yes. No. I want to have it on the side view.
You should.
Is it possible to? Huh?
You must do it yourself. I mean, from my side, I cannot change your shared screen.
No, side by side. No, then I don't have mine here.
You should just move to the next page. I mean, we now see the title.
Okay.
Page.
Yesterday this problem was not there. Anyway, if one could help me, if Vit or Vladimir could help me put this view. Yesterday for the whole day it was on the side by side one.
You must simply operate with your screen. I mean, what is visible here is what you are showed on your screen. So it's as if you change your screen to next page. You just go to next page in your viewer. You just click to the next page. Now I lost the shared picture, so you must share your screen. So now I see it again, so please just make your presentation the next page. You switch it off, but you should keep it on and you should move on your side. I mean, from my side, I just see what you show, so you must be showing on your computer.
Okay, I try it.
Next page.
Okay. So, okay, thank you, Milo, for your kind patience. Now I come to my topic. So I'm going to talk on this Wess-Zumino model, which is actually a supersymmetric field theory. So this particular theory, I chose this theory, is that this is of central importance in the theory of supersymmetry as well as in the theory of supergravity. And as I would explain, it plays a very, very crucial role. So for any theory to be a supersymmetric field theory, it has to remain invariant under certain supersymmetric transformations. And this particular model remains invariant under the so-called global or rigid supersymmetric transformations. So that is one thing. And what is the purpose of these supersymmetric transformations is that it rotates bosons into fermions and fermions into bosons. One more condition that is needed for a theory to be a supersymmetric field theory is that it must satisfy the so-called super Poincare algebra. This is a graded Lie algebra. So what you do is you extend the Poincare algebra by incorporating into it the supercharged Q. Supercharged Q is the generator of the supersymmetric transformations. So the super Poincare algebra would include not only the commutation relations of the generators of spacetime translations and Poincare generators, but it would also include the anti-commutation relations involving the supercharged Q. So this particular theory, Wess-Zumino model, as I would explain it shortly, satisfies both of these criterion. One can verify step by step everything. So
it's 2 o'clock.
It is invariant under the rigid or global supersymmetric transformations, and it satisfies the super Poincare. However, this theory is a non-manifest supersymmetric theory. What it means, you look at this theory in the first place, let me tell you that the contents of this theory, there is one scalar field, one pseudo-scalar field, and one fermionic field. So the scalar and pseudo-scalar fields, they transform under parity as the field A goes to plus A, then it's a scalar field. If field A transforms as minus A under parity, then it's a pseudo-scalar. One can also combine these two fields into one complex scalar field and accordingly write the supersymmetric transformations. So this actually, it was a very, very long story for the discovery of these transformations, supersymmetric transformations, because they are useful, extremely useful or crucial, I should say, in the superstring theory. They are also very crucial in the supergravity theory. So, taking this model as an example at the center, you see this, I am going to consider the theory in 4-dimensional Minkowski space. Okay, one can also consider it in that as a 2-dimensional model between one space, one time. What I would be presenting would be 3 space, 1 time dimensions in the Minkowski line. Now, so if one goes to 2-dimensional Wess-Zumino model, there is a straightforward generalization to the superstring theory, in particular, which is called as the RNS superstring theory or the Raymond-Naguswap superstring theory. This theory is an example of a non-manifest supersymmetry. So where you see this supersymmetry only at the level of the supersymmetric transformations. If you look at the action, you cannot imagine that this theory could be a supersymmetric theory. So that is the meaning of this non-manifest supersymmetry. But what one can do also for this particular case or in general, one can go to the formulation of superspace and superfields. So what you do, for example, for a 2-dimensional Minkowski theory, you extend the 2-dimensional Minkowski theory to 2 plus 2 superspace. So the measure of the theory becomes d2x into d2 theta. or d theta bar, where theta and theta bar are the Grassmann fermionic variables. So for four-dimensional theory like the Wess-Zumino model, if you want to construct a superspace formulation of the theory, then you extend the four-dimensional Minkowski space to 4 plus 4-dimensional superspace. So the measure of the theory becomes d4x times d2 theta a times d2 theta b, or d theta bar times d theta bar. And so now in this particular formulation, what happens? Every field of the theory, for example, a field phi or a field A, which is in Minkowski theory is a function of quantity x mu, now becomes a function of x mu and theta bar. If it is four-dimensional, 2 pairs of theta. So that is the idea. Now, so that means by taking this particular example and then going to two-dimensional free massless theory, and then one can go to superspace formulation of the theory, then this theory has a manifest supersymmetry, because you can see it directly at the level of the x and directly at the level of the field, because fields themselves are super fields and the action is a super action. The derivative, space-time derivative, d mu would be replaced by super covariant derivative, and so everything works fine, and this theory remains at the center of the considerations. Now, but another important aspect of this theory, this particular theory that I am going to consider is a theory with having global or rigid supersymmetry, and what one can do is one can construct a theory which has local supersymmetry. So what does it mean? A local supersymmetry theory actually turns out to be the supergravity theory. We would talk about it at some other point of time in some either full seminar or again in the conference next time. So supergravity theory is a theory that is local symmetry, and so conventionally you call a theory as supersymmetric field theory if it is invariant under rigid or global supersymmetry transformations. Here the transformation parameter is a constant Grassmann system. If you want to make it a local theory, then the transformation parameter would have to be made a function of x mu. So then that becomes a local symmetry, and that actually turns out to be supergravity theory. When you make the transformation parameter, here I have shown symbolic, it is not specific model dependent. In general, a supersymmetry transformation rotates bosons into fermions and bosons, or in a very simple manner, we can say that it relates bosonic and fermionic variables. So the transformation parameter, this epsilon bar here or this epsilon here, they are constant Grassmann spinors. So here I am saying emphasizing on constant. So here the epsilon and epsilon bar are constant Grassmann spinors. For constructing a theory, this would be a rigid supersymmetry transformation. I will show it explicitly for the Wess-Zumino model in a few minutes. And so here, this delta operator is bosonic, B is bosonic, epsilon bar is fermionic, F is fermionic. So F is fermionic, epsilon is fermionic. Now this del here, which is del mu actually, which is the space-time del. This has a very deep hidden importance, because this transformation involves this space-time derivative of G. It actually has a deeper meaning that the supersymmetry transformations here, they are not to be viewed as some kind of internal symmetry transformations, but they are to be viewed as a Poincare space-time symmetry. So here, super Poincare space-time symmetry, that is the indication of this presence of delta field here. And so if one wants to so the understanding of supersymmetric field theory is important by themselves, by itself, as therefore I have chosen this particular model. And now, but you see, for constructing the so-called supergravity theory, this is only the one elementary step that you have to have your transformation parameter to be space-time dependent, but this alone does not solve our problem. There is a standard procedure which is called as Newton's procedure for constructing a theory in local symmetry. This is called by the name gauging a global symmetry into a local symmetry. So this Newton's procedure is very well known. This is how we construct our quantum electrodynamics, for example, the simplest theory. So if you consider a theory for the complex scalar field, then what you do, you replace your space-time derivative du by the covariant derivative. And so before you do that, that theory has invariance under global symmetry, which are called as the U1 phase transitions, U1 phase symmetry. But now you replace the du by the covariant derivative. So you, in the process, you introduce an extra field, which is called as the gauge field. In the case of quantum electrodynamics, this field, gauge field, is just a U1 gauge field, a nu. But then, that is also not enough, but then you have to make this field, extra gauge field that you have introduced to be dynamical. So what you do, you have to introduce a kinetic energy term for this particular extra gauge field. Now, what happens here, the same actual considerations also hold true for the, if you want to gauge the massless fermionic field, and from there you obtain quantum electrodynamics. So here also you follow the same procedure, introduce covariant derivative, introduce extra field, human gauge field, and then make dynamical to write down the kinetic energy. Now, this particular thing, I'm working on a full semester lecture notes on supergravity theory. At some point of time, I'm supposed to give 2 semester lectures courses on supersymmetry, which means rigid, and supergravity. So, theory of supersymmetry and supergravity, possibly. So this, because of pandemic, I couldn't do it. I was supposed to do it at Oldenburg, but I'm looking forward to normal times to come back. So now, when you do consider the Wess-Zumino model, and then you want to gauge the global symmetry of the theory, what you have to do, you have to introduce the covariant derivative. In this case, it will be super covariant derivative, and the extra gauge field that you introduce would be a spin 3/2 field. That is called as the Gravitational Field. So that's very important, and this then. The gravitational field is the extra gauge field that you have introduced. You have to make it dynamical, so you introduce kinetic energy term for this spin 3/2 field. That is called as Rarita-Swinger action. And of course, for supergravity, you also have the metric to be dynamical, which means that the theory must remain invariant under general coordinate transformations, which vary from point to point in the space-time manifold. So that is the point. So I think I would leave you there with this, and then I would like to proceed further with these models. So at the moment, let us just stick to so-called supersymmetry. If I have time at the end of my talk, I might again go back to local supersymmetry. So right now if we consider 2 consecutive infinitesimal rigid global supersymmetry transformations of a photonic field, so like that, delta 1b is epsilon 1 bar a, and so on, then what you find that the 2 internal SUSY transformations lead us to a space-time translation. We have to carefully look at the right-hand side, which involves a space-time derivative of this photonic field A. Okay, this A being is just a force current like psi bar epsilon psi. Here, epsilon 1 and epsilon 2 are transformed. spinors, but they are constant spinors, not the Dirac spinors. I would explain later. So this is also an indication that right now I have not derived this, but I would later on show that explicitly we can find this anti-commutation relation of the two supercharges QA and Q bar to be dependent on this capital P mu. This P mu is the generator of the Lorentz translations. Okay, so you see that if you apply two consecutive supersymmetry transformation, then the generator of the supersymmetry transformation, which is QA, which by itself is a spinor field, it gets related to the space-time generators of the Lorentz group. So this is a very important result, which eventually tells us that supersymmetry transformations are really an extension of the Poincare space-time symmetry, which is actually the external symmetry and not to be counted as internal symmetry. So supercharges do not generate internal symmetry, but they generate external Poincare space-time symmetry. That is the main point. Now let us have a look at what is this model like. So here I have a field A, which is a scalar field. It's a massive, so I put mass term. B is a pseudo-scalar field. This is also massive, so I put a mass term. Then these are some coupling terms. If you take this A inside, then this is AQ, this is A into B square. So wherever you have, even actually these are also mass terms, according to me, are also coupling terms, where a field is coupled to itself at a point that gives rise to the mass term of the field here. So, and here you consider A to the 4, B to the 4, A square into B square, etc. You also find some terms like the scalar field coupled with the psi bar psi. Psi is the fermionic field, and we need to understand what it is. So this is, I would explain, I would like to thoroughly explain what it really means. And so M and G are the mass and coupling disciplines used in this model. For Wess-Zumino model, when of course A and B are scalar and pseudo, psi is a spin one of Majorana. So what is a Majorana spinor? Where we impose psi equal to psi c, and which is c times psi bar. So this is just transpose of the Dirac conjugate. So actually psi bar is the Dirac conjugate of psi, and psi c is the charge conjugate of psi. These are two different things. This c is the charge conjugation matrix. C is the charge conjugation matrix, which depends on the choice of representation of the gamma matrices. However, for all representations, including Dirac, Weil, Majorana, these properties are always fulfilled by irrespective of which representation you choose for the gamma matrices. So what is important here is that in this model, this psi is a Majorana spinor. So this obeys this condition psi is equal to psi. So it describes fermions that are their own antiparticles, or it maps particles to antiparticles. And this mass M and strength G, they remain the same for every term. Whichever term, if you don't want to consider a particular term, it does not matter. But if you want to consider even more complicated couplings, G would remain the same. Okay, this is one crucial point. Now, let me talk about this special vector, which is called as polyluance. We already know about this vector P mu. So if you take a square of P mu into P mu, then P mu, P square is a Casimir operator. And this is important because W square is also a Casimir operator. These are the only two Casimir operators in the theory of supersymmetry. And what is a Casimir operator? An operator that commutes with the M mu nu, which is the generator of the Poincare symmetry, and this is the Lorentz translation. So it commutes P square commutes with P mu as well as with M. The same is also true for W square. Now, I have been interested in these Casimir operators. There is a very, very deep meaning to it. P square has the eigenvalues M square greater than 0. W square has the eigenvalues minus M square into S into S plus. So these are the eigenvalues of P square and W square. And here S denotes the spin of the representation. And it assumes discrete values 0, 1, half, 1, 3, half, and so on. So a representation is it is denoted by M and S. So M and S are the mass and spin of the representations. What it physically means? It physically means that a physical particle would have the rest mass M and spin S. For the spin S, I would have been a little bit further. So these are very, very interesting things. So this I have already explained that all the fields, they have the same mass and they couple with the same spin G and so on. Now, let us look a little bit further. We find that this Polylubansky vector is proportional to P mu. And this constant of proportionality, so I can write it for the time-like components of this. I can write lambda equal to P dot J by P0. P dot J is the time-like component of the Polylubansky vector, which you obtain from its definition. And this lambda is plus minus S, which is the spin of the representation. So this is very, very, very crucial. And actually, this helicity plays a very central role when you go to, in the supergravity theory, when you go from n equal to 1 supersymmetry to n equal to 8 supersymmetry. In n equal to 8, n equal to 1, there is only one supercharger. In n equal to 8 supersymmetry, there will be 8 superchargers. So you can, with the help of this, you can construct the particle contents of the theory. I postpone it to the end of my talk if I have time. So n equal to 1 is minimal supersymmetry and greater than 1 extended supersymmetry. Now I just write this theory, free theory. So I put G equal to 0 the coupling. I drop all the terms that involve coupling. And if I were to, so this is the free field theory for the model.
You have 10 minutes.
10 minutes, yes, great, thank you. So the main concepts I think I have covered. Now the things are simple. Or one has to consider mass less than 1 or and 0. Now these are the supersymmetry transformations and they are rigid. So psi, epsilon bar, epsilon everywhere, they are constant. Now one thing, delta psi and delta psi bar, they are not independent, but they are dependent on each other. One can be obtained from the other. This is the main point here. And because, so you see for the first time, you see the action of the Wess-Zumino model, and now you see these transformations. So I must mention the names of Gervais and Sakita. Gervais has been to India, and I took him around to some places from École Normale Supérieure in Paris. And on the other hand, from the Russian group, Golfand and Lichten, they also discovered independently these transformations. So some decades ago, this was a very serious discovery that otherwise the string theory could not have progressed at all, because you find the same symmetry in the RNS supercurrent theory. So you can construct the conjugate current, which is the supercurrent, and it is proportional to K mu and epsilon bar. Epsilon is a fermionic, so K mu also has to be fermionic. It is indeed fermionic. There is one Fermi field sitting here side and no other. So this supercharge, this is the charge density, this is the supercharge. So supercharge is fermionic, but overall charge supercurrent is both fermionic. And now taking these expressions for QA, you can explicitly derive this relation, anti-commutation relation of QB, the rejected thing. This is the super Poincare algebra. So commutation relations of P mu with P mu and P mu with M mu. But of course, always bosonic quantities and fermionic quantities, they would commute. But these fermionic quantities to QA bar, QA bar. So this super Poincare algebra has 14 generators. 4 generators of translations P mu, 6 generators of Poincare transformations that include angular momentum as well as the Lorentz boosts, and 4 spinors. Spin charges. So now, if you want to consider the theory to be massless, you put M also equal to 0. This It actually, if one replaces this A by a vector valued function field, and if one replaces psi also by a vector valued field, then this gives you the action or the Lagrangian for the RNS supersymmetry, where that alpha, if you put alpha as vector in text, then that spans the target space or the space of the space-time magnetic, which is 10-dimensional for supersymmetry. So this we have discussed already. Now this corresponds to G equal to 0 as well as M equal to 0. In this M bar on here, prior to this, still back, M bar on 0, but now you can do M also to equal to 0, and delta psi and delta psi bar as usual, they must be independent. They must not be independent. A and B could be combined into phi and phi star in that manner, and these supersymmetric transformations be rewritten. So these are the supercharge and the supercurrent for the massless free best order. Now let me come to the last part. I take 2-3 minutes. So here this first two terms, they constitute the bosonic part of the Lagrangian. Last term constitutes the part of the Lagrangian. Now, fermionic part of the Lagrangian could be written in two alternative ways, L1 and L2. And these two differ by a total derivative. It's a textbook calculation. They are seen to differ by a total derivative. So this by that I mean that the two describe the same theory. However, let us see some subtle differences. With L1, I get pi bar equal to 0, but pi as non-zero. What it means? It means that pi and pi bar are independent fields, so they are not dependent. And correspondingly, I could get two primary constraints. I can find their matrix of the Poisson matrix. I can quantize the theory. And in fact, the contents of L1 and L2 both are the same, but so there are some differences in the interpretation. Now, if I take L2, then my pi comes out to be this and pi bar comes out to be this. So here you can see that pi bar is just the Dirac conjugate of pi. So they are dependent fields, they are not independent. That is one thing. And moreover, additional difference that is going on with us is that is all psi bar, pi bar, they are all Majorana spinors and not Dirac spinors. Okay. So now if we consider the entire Wess-Zumino model theory, not only fermionic part, then these are the momentas pi A, pi B, pi and pi bar. And in this manner, we get, there are only two constants. These are expressible, here is the velocity, but here there is no velocity, So there are two primary constants, and in fact, they are the only constants. In fact, Chi1 and Chi2 represent an infinite number of primary constants, which could be labeled by alpha and beta, but I omit these for simplicity. You can construct in the standard manner using the Legendre transformation, the canonical Hamiltonian, total Hamiltonian, just now like we saw constructed. Then you can calculate the matrix, the Poisson brackets of the constants. It would be a 2x2 matrix, and the non-vanishing elements. And the determinant is important because it goes into the definition of the construction of the path integral of the theory. So these, you see, the commutation relations here and these anti-commutation relations, they look just the usual ones that you would obtain in, for example, here in scalar field theory, and this they look just identically the same as you would obtain them in the Dirac theory, but here psi is equal to psi c. So these spinors, they are not Dirac spinors, but they are Majorana spinors. So Majorana spinors have only real elements in it. So this is one important thing. Now, for the path integral quantization, you have to write down the transition of the theory from vacuum to vacuum, which at the S matrix level would correspond to t equal to minus infinity to t equal to plus infinity. So, and you consider the external sources like JK here for the present theory, and then you can write down the transition amplitude or the generating functional of the theory. This actually, after the first term, this is the first order Lagrangian density of the theory. And this d mu is the measure of the phase space, which includes here the square root of the absolute value of the determinant of the constraints of the theory. And these are the constraints of the theory. So that completes both the Hamiltonian and the quantization of the theory. I think the last slide. So let me just make two remarks like the how far we have gone when we start from relativistic quantum mechanics, Dirac equation. So in relativistic quantum mechanics, Dirac equation is a single particle relativistic wave equation, and psi is a wave function. What happens in field theory when I write down Dirac action or Dirac Lagrangian? I vary the action and I obtain Euler-Lagrange equations of motion, and they are identically the same as the earlier Dirac equation. But conceptually now, field psi is a field. It was a spinner also here, it was also a spinner here, but here it was not field, but was a wave function. Here it's a field, and so it's a spinner field. But now we have gone a little bit beyond these two steps. That is, we are now in the Wess-Zumino model. So this is a supersymmetric field theory, and here we have imposed that psi is equal to psi c. The charge conjugate of psi is the same as psi. So this spinner psi becomes a Majorana spinner, and it's no longer the Dirac. And that essentially puts me at the end of my talk. These points I have covered earlier, but if somebody asks the questions, like you can easily extend this to RNS superstring theory, to Green-Schwarz superstring theory through the formulation of superspace and superfields, and you could go to supergravity theory by using the Neodor's procedure, by gauging the global symmetry of this model to a local symmetry, the Neodor's procedure, and by introducing a super covariant derivative, and then making the gauge field here is a spin 3/2 field Gravitational field. You make it, I wish I had another half an hour or 20 minutes, then I would have obtained n equal to 1 supergravity theory, but we postpone it for future. So, you have to make the gauge field, Gravitino gauge field, as dynamical. So you have to add a kinetic energy term for the Gravitino field, but you also have to make the metric of the theory to be dynamical. How do you do that? You have to give it a kinetic energy term that comes from the Hilbert-Einstein action that provides the kinetic energy to the graviton, and Rarita-Swinger term gives kinetic energy to the Gravitino field, and this is how we go about it. But if you have only n equal to 1 supergravity, then there is only 1 graviton and 1 gravitino. But if you have n equal to 2 supersymmetry, you have 1 graviton and 2 gravitinos and 1 photon, 2 supercharges. That was the Einstein's string theory. But if you have n equal to 8 supergravity, then there would be 8 supercharges, and you will have a very beautiful spectrum. It will go from that I had explained the concept of helicity. So my first graviton would have spin +2, then you keep reducing it by 1/2. So +2, +3/2, +1, +1/2, 0, then -1/2, -1, -3/2, and -2. So this is a complete theory. N equal to 8 supergravity would be a complete theory, having 2 gravitons also with the negative. So one could even think of that state to be some kind of a superparticle having all these states as the different polarization states of that graviton. And one can calculate the number of these, how many gravitons, how many gravitinos, how many spin 3/2, spin 1/2, spin 1, spin 0 scalar.
Yeah, so let me remind
you. Yes, thank you so much. Thank you so much. Milo. I think you have been extra kind to me. So my extra thanks.
So you had extra time, which you used very well. Thank you for your nice review of the field, and
because unfortunately the timing in India and in US are different. So people, specialists in field theory from US, are still happily sleeping. So I am not sure if there will be some questions. I recommend that because of time, we now are well over time. So we should.
Milo, let me mention one line. Let me add one line.
Okay,
that
but
my,
there will be no space for
my video lectures on superstring theory are available on my YouTube channel. If one writes my name in the YouTube, Daya Shankar Kulshrestha, one gets to my YouTube channel, and almost 50 hours of lectures on superstring theory are there.
So in this sense, it was better than asking questions because now everybody can ask. So thank
you.
So
I would welcome everybody to watch my.
Okay, so thank you very much for your very well done review. And now I declare the coffee break, and we shall meet according to the timetable at 11:30. So thanks to the speakers of all talks today, and let's look forward to the continuation of the conference. So thank you, Daya.